Right, this is the first of two videos on this idea of hypothesis testing, which the two videos kind of go together, and one of the key ideas is understanding what a hypothesis test is, and in which we make one of two hypotheses, an alternative or a null hypothesis, and then come up with a statistical measure to determine which hypothesis is correct, and then eventually make a conclusion. So I'm going to work through this example here in which we look at the number of students in an IB students who have enrolled for in either economics, geography, or history, or biology, chemistry, and physics. And economics, geography, and history are what we call Group 3 HL courses, and Group 4 courses are biology, chemistry, and physics. And we want to determine if the decision to take the decision to take a particular economics, geography, or history course is somehow dependent on the decision to take a particular biology, chemistry, or physics course, or if they are just all independent, if there's no sort of relation between students who take one course if they take others. And again, for my example here is, for example, students who take economics tend to more often take physics. If that's the case, these two are not independent of one another. But if that's not the case, they may be. With that said, first we need to make our hypotheses. And we always have two types. So we start with the null hypothesis, which is denoted H with a subscript 0. And that is always the hypothesis that there is no connection, or that, in this case, they are not dependent of one another. Or another way of saying that, if I put for H naught, for my null hypothesis, this is that the choice of taking either a Group 4 or Group 3 course is independent of one another. So if this is the case, and our null hypothesis is always the idea that it's our default position, and we're trying to prove this is not true. But if this is the case, then students, it doesn't matter if they take economics, geography, or history, we should not see a relation to certain students taking more of one of these three. That's it. That's the null hypothesis. The alternative hypothesis, which we denote H1, is the complement of this. It should leave no other options. So if the null hypothesis is that the choice is independent, well, then for H1 you could say the choice is dependent of one another, or even better is just to say the choice is not independent. So I'll say the choice of Group 4 or Group 3 is not independent. And so in general, our null hypothesis should always be the default position. It should always be the position that we are trying to prove is not the case. And we want to set a fairly high standard to prove that it's not the case. And there should be no other options. So they either are independent or they're not independent. There's nothing else. There's no other options. There's no H2. All right, so this is the data we have, and we call this data up here the observed data. This is the data we have on this. And it's hard to tell by looking at this much of if there's any sort of signs of dependency here. So what we want to look at now is make a new table of the expected values. The expected values are the values that we'd have if there is no dependency between these courses. And so, for example, for what would go here, the expected value for the number of students who take economics and biology, the way we always calculate it is we take the total number of students in the economics column times the total number of students in the biology column. We multiply those together, and we divide by the total number of students altogether. So in this case, it would be 50 times 86 divided by 200. And that leads us to 21.5. So our expected value for that is 21.5, which means just mathematically, if there is no dependency at all between the courses students take, if it is all truly independent of one another, we would expect among 200 students, in this case, to have 21 and a half students enrolled in that. Obviously, you're not actually going to have a half. The difference is what we want to eventually look at is how these values differ from the observed values. If you do the same thing, I'll just do another example. If I want to find this one here for chemistry, I want to multiply 74 by 50 and then divide by the 200. And I should get 18.5. If I want to find this one here for geography and biology, I want to multiply 100 by 86 and divide by the 200. And you would get 43. So a bit of practice, it's a pretty quick calculation. I have 9 blanks to fill in. I'll just fill in all the rest. All right, so again, for this last one, that 10 was found by going 50 times 40 and dividing by the 200. All right, so now if I look at my expected table compared to my observed table, there's differences. That is to be completely expected. Just because there's differences doesn't mean that there's dependency. The question is, how much do they differ? And how much of that is just from chance, and how much is it really unlikely that it's just chance? And for that, we want to calculate what we call the chi-squared statistic. And we can do this in 2 ways. One is by using a formula, which I'll mention. One is by using our GDC. And so the formula I'm going to use is right here. If we want to find the chi-squared statistic, it's the sum of the difference between any particular observed frequency from its expected frequency. You square that and then divide by the expected frequency again, which again, perhaps looks more complex. It can be a little tedious, but in this case, if I want to find this statistic, maybe I'll write it right here. So chi squared, it's going to be, again, the sum of observed minus expected squared over the expected. So for example, the first one I'd look at is, it doesn't really matter what order I subtract, so I'm just going to square it, but observed 25 minus 21.5. Then I square that, and then I divide by the expected amount, 21.5. So that's my first term. It would be 25 minus 21.5 squared divided by 21.5. And I do that for all of these. So the next one, I would go 15 minus 18.5. Square that and divide by 18.5. And keep going for all of these 9 cells until the last one I'll just mention here. If you did that one last, I'd be comparing 20 and 10. A pretty big difference. So 20 minus 10, square that, divide by 10. And if I did that for all of them, we would get approximately 20.39, which is a measure of how far the observed results stray from the expected results. In its own, it doesn't really tell us too much, but that is the chi-squared value. So before I can do more with that, I also realize that what I just did is kind of time-consuming, and computers are good at doing things that are time-consuming. And so you should be able to use your GDC to calculate both the expected values and the chi-squared value. On most GDCs, you need to create a matrix. You'd create a 3x3 matrix. You would substitute those values into the matrix. Depending on your GDC, how you exactly determine it is, you need to be specific. You need to be familiar with your GDC. And in general, though, it can create a new matrix with all the expected values, as well as this chi-squared value, as well as a p-value. And so let me write down these. So ideally, again, you use your GDC. Again, you should see on your GDC, the chi-squared value is about 20.39. But you also have this p-value, which is approximately 4.18 times 10 to the negative 4, which, keep in mind, out of scientific notation is 0.000418. So what does that mean? That means there's the probability of these observed results happening by chance, or the probability of these results occurring based on these totals in which there is no dependency, is 0.000418. which as a percentage is 0.04, about approximately 0.04% probability that these results would occur without any dependency. That's a very low amount. So does that tell us if these are dependent or not? Well, in general, before I can make a conclusion, we really want to decide before the start, what is our level of confidence we want to accept. Because if we want to prove, if we want to state that this is the case, or even better, if we want to reject this, then we need to have some significant statistical data. And in general, before we perform any statistical analysis, we want to decide on a value for our p-value that we feel is appropriate that we can make a confident decision. It is subjective. A common p-value is this, and we usually denote it with the letter alpha, is 0.05. So this represents a 5% probability. And there is no rule though, but this is quite common. And really going forwards, this should always be stated before we come to our conclusion. We don't want to get our data and then make a conclusion based on that. We want to come up with our level of confidence in advance, then see our data, and then decide if it met that threshold. However, this is a very common level of confidence. And so I can see that our p-value of 0.000418 is definitely less than 0.5, which means this far exceeds our threshold for what we would deem as being a confident level that we would accept as saying this is not just chance. So at this point, this means that we reject H0. We reject our null hypothesis and accept H1, the alternative hypothesis. Which really what we're saying is we are now saying statistically, we are accepting the notion that a student's decision in which group 3 or group 4 class is not independent. So we are saying we have statistical evidence that the choice that students choose kind of depends on what their other group choice was. So we have statistical evidence that, for example, students who take geography take at least one of these more or less likely than another. And we have evidence for that. And again, our evidence shows that this probability tells us right here that it seems extremely unlikely that we would see values like this just by chance. Extremely unlikely. But that said, we'll continue this idea in the next lesson.